In the high-stakes theater of modern aerospace dominance, few operational concepts have generated as much intrigue, skepticism, and genuine technical bewilderment as the Mikoyan MiG-41, officially designated under the program code PAK DP, which stands for Prospective Air Complex for Long-Range Interception. This proposed aircraft, a machine that currently exists in the nebulous space between ambitious engineering white papers and the aspirational declarations of the Russian defense establishment, represents the Russian Federation's attempt to reclaim the high-altitude dominance once held by the Soviet Union's legendary MiG-25 Foxbat and MiG-31 Foxhound. The MiG-41 is not merely a procurement project. It is a symptom of strategic anxiety, a technological Hail Mary designed to close a rapidly widening capability gap in the defense of Russia's vast northern frontier against a new generation of hypersonic and orbital threats. To understand the MiG-41, one must first strip away the layers of hyperbole that often accompany Russian military announcements and examine the machine through the cold lens of physics, engineering constraints, and strategic doctrine, for the claimed specifications read less like a standard defense procurement document and more like the wish list of a futurist unburdened by the laws of thermodynamics or the realities of a sanctioned industrial base. Speeds exceeding 4.3 times the speed of sound, operational ceilings grazing the mesosphere, directed energy weapons capable of swatting hypersonic missiles from the sky, and the ability to operate as an anti-satellite platform. Yet, dismissing the project entirely as vaporware ignores the genuine doctrinal requirements that drive its development, as Russia possesses the longest border in the world, a significant portion of which lies along the frozen, desolate expanse of the Arctic, a region that is becoming increasingly militarized and accessible due to climate change. This region is the shortest route for American strategic bombers and cruise missiles to reach the industrial heartlands of the Urals and Siberia, and the current guardian of this airspace, the MiG-31, is approaching the twilight of its operational life. The PAK DP program is tasked with a mission that is fundamentally different from Western sixth-generation fighter programs like the U.S. Air Force's Next Generation Air Dominance or the U.S. Navy's FAXX. While Western programs prioritize broadband stealth, sensor fusion, and collaborative combat aircraft to penetrate contested airspace, the MiG-41 is envisioned as a defensive shield, a high-speed, high-altitude interceptor designed to deny the enemy access to the near-space domain. It is a platform built to solve a geometry problem: how to position a kinetic interceptor in front of a target, moving at 10 times the speed of sound, such as a hypersonic glide vehicle, before it strikes critical infrastructure. And the answer, according to Mikoyan Design Bureau engineers, is an aircraft that is effectively a reusable first-stage booster, capable of dashing at hypersonic velocities to extend the kinematic range of its missiles. The genesis of the MiG-41 cannot be separated from the legacy of the Soviet Air Defense Forces, for unlike Western air forces, which historically emphasized air superiority fighters capable of dogfighting and expeditionary warfare, the Soviet Union maintained a separate branch of service dedicated solely to the defense of the homeland. The doctrine was dictated by the tyranny of geography, where defending the millions of square kilometers of Siberian airspace against high-altitude threats like the B-70 Valkyrie and the SR-71 Blackbird required an aircraft that prioritized raw speed, range, and radar power over maneuverability. The result was the MiG-25 Foxbat, a steel brute capable of 3 times the speed of sound, and its successor, the MiG-31 Foxhound. The MiG-31 was a quantum leap in capability, introducing the Zaslon phased array radar, which allowed it to act as a flying AWACS, tracking multiple targets and sharing data via secure data links to coordinate Wolfpack intercepts. The MiG-31 remains the fastest operational combat aircraft in the world, with a top speed of roughly 2.83 times the speed of sound, and arguably the only platform currently capable of carrying heavy hypersonic munitions like the Kinjal. However, the MiG-31 fleet, produced between 1975 and 1994, is aging, and the structural fatigue accumulated from decades of high-speed patrols, combined with the obsolescence of its engines, masterpieces of 1970s engineering that are increasingly difficult to support, means the fleet faces a hard stop in viability by the mid-2030s. The urgency for the MiG-41 stems from the shift in the threat landscape, where the subsonic cruise missiles of the late Cold War are being supplemented by hypersonic glide vehicles and scramjet-powered cruise missiles that fly at altitudes between 30 and 100 kilometers, too high for most surface-to-air missiles to engage effectively and too low for exo-atmospheric interceptors. This near-space domain is the new high ground. A conventional fifth-generation fighter like the Su-57, with a service ceiling of roughly 20,000 meters and a top speed of twice the speed of sound, is kinematically defeated by these threats, as it simply cannot climb high enough or fly fast enough to impart sufficient energy to its air-to-air missiles for a successful intercept. The MiG-41 is conceptually designed to fill this void by operating at altitudes up to 50,000 meters and speeds exceeding 4 times the speed of sound, effectively compressing the engagement timeline and restoring the look-down, shoot-down advantage that the MiG-31 held over cruise missiles, but applying it to the much faster, higher-flying threat of hypersonic weapons. This requirement for near-space operations is not merely about altitude. It is about mastering a flight regime where the atmosphere is too thin for conventional aerodynamics, yet too thick for orbital mechanics, a domain where thermal management becomes the primary design constraint. The most controversial and technically demanding claim regarding the MiG-41 is its projected top speed of 4 to 4.3 times the speed of sound, approximately 4,900 to 5,300 kilometers per hour. To appreciate the magnitude of this challenge, one must look at the thermal environment, often referred to as the heat thicket, where aerodynamic heating is not linear. It scales with the square of the speed, and at hypersonic speeds, chemical dissociation of air molecules begins to add additional thermal loads. At 3.2 times the speed of sound, the SR-71 Blackbird experienced average skin temperatures of roughly 260 to 300 degrees Celsius, with localized hotspots at the nose and leading edges exceeding 500 degrees, necessitating a structure built of 85% titanium and 15% composite materials, as standard aerospace aluminum loses its structural integrity at roughly 150 degrees and melts at 660 degrees. At 4 times the speed of sound, the stagnation temperature at the nose cone and wing leading edges rises exponentially, and research into hypersonic vehicle leading edges at 5 times the speed of sound indicates heat fluxes that can reach 40 kilowatts per square meter, generating surface temperatures that can exceed 1,000 degrees Celsius, depending on the specific trajectory and duration of flight. Even the nickel-steel alloy construction of the MiG-25, which allowed it to survive short bursts of 3.2 times the speed of sound at the cost of wrecking its engines, would be insufficient for sustained operations at 4 times the speed of sound. The MiG-41 would require extensive use of exotic materials, far surpassing the titanium used in the Cold War, pointing towards the necessity for advanced ceramic matrix composites, carbon-carbon structures, and perhaps actively cooled leading edges, where fuel or a specialized coolant is circulated beneath the skin to carry away heat, a technology typically reserved for rocket nozzles and experimental scramjets. The claim that the MiG-41 will be a stealth aircraft complicates this further, as traditional radar-absorbent materials are polymer-based and would burn off or delaminate under such extreme thermal stress. The challenge of 4 times the speed of sound flight extends beyond preventing the airframe from melting. It involves maintaining structural rigidity while the aircraft expands and contracts, and the cockpit canopy presents a specific critical point of failure. Traditional acrylic or polycarbonate canopies used on fighters like the F-22 or Su-57 would soften and fail under the aerothermal loads of 4 times the speed of sound. likely requiring the MiG-41 to use a specialized quartz or glass ceramic composite canopy, similar to those used on the X-15, which are heavy and optically complex. Or alternatively, the aircraft might feature a virtual cockpit, burying the pilot deep within the fuselage for protection and relying on external cameras and sensors to provide situational awareness. While renderings show a conventional bubble canopy, engineering dictates that a true hypersonic interceptor would likely have a very different, flush-mounted, or heavily reinforced visual system. The aerodynamic configuration shown in leaked design concepts often depicts a flying wing or a blended wing body design with twin vertical stabilizers, bearing a superficial resemblance to a flattened F-35 or the Su-57, but with more aggressive sweep angles. This configuration attempts to reconcile two conflicting requirements: low observability and high-speed performance. Supersonic flight favors sharp, thin leading edges to slice through shock waves, minimizing wave drag, while stealth favors rounded, blended edges to deflect radar waves continuously. At 4 times the speed of sound, the wave drag penalty is severe, so the MiG-41 would need a highly swept planform, likely a delta or cranked aero variant, to keep the wings inside the shock cone generated by the nose. The integration of the intakes is particularly critical. They must manage the violent shock waves of incoming air to slow it down to subsonic speeds before it hits the engine face, all while maintaining a low radar cross-section. This suggests the use of complex variable geometry ramp intakes or sophisticated carrette inlets that are optimized for a specific speed, potentially sacrificing efficiency at lower speeds. The single greatest technical hurdle for the MiG-41 is the engine. Conventional turbofan engines, even advanced variable cycle examples like those developed for the Su-57, hit a hard thermodynamic wall around 2.5 to 3 times the speed of sound. As speed increases, the air entering the intake becomes compressed and heated by the shock waves, and by 3 times the speed of sound, the air is so hot that adding fuel in the combustion chamber provides very little additional energy, while the temperature limits of the turbine blades are exceeded. The MiG-31's engines, massive low-bypass turbofans, are essentially rockets with a compressor attached, yet they are redlined at 2.83 times the speed of sound. Pushing them to 3.2 times the speed of sound is possible only in emergencies and typically results in catastrophic engine damage requiring total replacement. To achieve sustained flight at 4 times the speed of sound, the MiG-41 cannot rely solely on a turbofan. The consensus among aerospace analysts is that the PAK DP must utilize a combined cycle propulsion system, likely a turbo ramjet or a turbofan, with a bypass capable of operating as a ramjet. In this configuration, the engine operates as a standard turbofan for takeoff, landing, and subsonic cruise. But once the aircraft accelerates past 3 times the speed of sound, the mechanical compressor and turbine are bypassed or neutralized, and the incoming air is diverted directly into the afterburner section. The sheer forward speed of the aircraft compresses the air, known as the ram effect, and fuel is injected to produce thrust. This concept was partially utilized in the engines of the SR-71, which bled air from the compressor directly to the afterburner at high speeds, but those engines were limited to 3.2 times the speed of sound, and pushing to 4.3 times the speed of sound requires a much more robust ramjet mode, and, crucially, a mechanism to manage the mode transition. The transition from turbojet to ramjet is a region of aerodynamic instability. If the shock wave inside the inlet is not perfectly positioned, the engine can suffer an unstart, a violent event where the internal pressure forces the shock wave out of the inlet, causing an immediate loss of thrust and potentially yawing the aircraft apart. More exotic reports suggest the potential integration of a pulse detonation engine, Unlike traditional jet engines that burn fuel via subsonic combustion, a pulse detonation engine operates by detonating fuel in rapid supersonic pulses, generating immense thrust and theoretically offering more efficiency at high speeds. While Russia has conducted research into these engines, integrating such a violent high-vibration propulsion system into a manned airframe presents immense challenges in terms of structural fatigue and pilot endurance, as the noise and vibration would be deafening and potentially destructive to the sensitive avionics required for a sixth-generation fighter. Given the current state of Russian engine manufacturing, which has struggled to mass-produce engines for the Su-57, it is highly probable that early prototypes of the MiG-41, if they materialize, will be powered by uptuned derivatives of existing engines, likely limiting them to around 3 times the speed of sound, with the true 4 times the speed of sound capability reserved for a future engine that may never arrive. The primary mission of the MiG-41, intercepting hypersonic missiles, presents a targeting nightmare, as a target moving at 10 times the speed of sound creates a plasma sheath that interferes with radar, maneuvers unpredictably, and closes the distance in seconds. To counter this, Russia is developing a multifunctional long-range interceptor missile system. This system represents a paradigm shift in air-to-air combat. Instead of a single missile attempting a bullet-hitting-a-bullet kinetic kill, the concept functions as a missile bus, where the MiG-41 launches a large, heavy booster that travels to the predicted intercept zone, releasing a cluster of smaller, highly agile submissiles. These submissiles utilize their own active seekers to create a kill web or a cloud of kinetic interceptors, significantly increasing the probability of a hit against a maneuvering hypersonic glide vehicle. It is the aerial equivalent of using a shotgun instead of a sniper rifle to engage a fast-moving, erratic target. For long-range engagement of conventional targets like AWACS, tankers, and bombers, the MiG-41 will rely on massive weapons weighing 600 kilograms with ranges of up to 400 kilometers and speeds of 6 times the speed of sound, utilizing a lofted trajectory to climb to the stratosphere to minimize drag before diving on their targets. Successor missiles are rumored to be hypersonic weapons designed specifically to fit inside internal weapons bays, with claimed ranges exceeding 300 kilometers and speeds potentially reaching 7 to 9 times the speed of sound, allowing the MiG-41 to engage high-value targets from well outside the retaliation range of NATO fighters. The combination of the MiG-41's launch speed of over 3 times the speed of sound and the missile's own propulsion would give these weapons an immense kinematic advantage, extending their no-escape zone significantly compared to a launch from a subsonic platform. For medium-range engagements, particularly against highly agile or stealthy targets like the F-35, the MiG-41 is expected to carry missiles with active phased array antenna seekers. Traditional missile seekers use a mechanical dish that physically moves to track a target, which has mechanical lag and a limited field of view. But these advanced seekers use electronic beam steering, allowing them to instantaneously adjust their tracking beam. This theoretically prevents an enemy fighter from breaking the lock with high-G maneuvers, as the seeker can track the target's movement faster than the missile frame can physically turn, guiding the interceptor to a collision point with ruthless efficiency. Perhaps the most futuristic claim surrounding the MiG-41 is the inclusion of an electromagnetic pulse cannon or anti-missile laser systems. An electromagnetic pulse weapon would fire a burst of high-power microwave energy to fry the sensitive electronics of incoming missiles or enemy aircraft, effectively neutralizing them without a kinetic hit. While theoretically possible, the physics of power generation on a fighter-sized platform make this incredibly difficult, as generating a weaponized electromagnetic pulse or a laser beam powerful enough to damage a missile requires megawatts of excess power. This would necessitate an auxiliary power unit of unprecedented size or supercapacitors that take up valuable internal volume and add significant weight. Given that thermal management is already the primary constraint of the airframe, adding a megawatt-class heat source seems counterintuitive unless the plasma stealth system also serves as a mechanism for managing this energy. Now, before we continue, I want to hear from you. Do you think the MiG-41 will be a revolutionary game-changer in aerial warfare, or is it destined to remain an ambitious concept that never takes flight? Drop your thoughts in the comments below, and if you're enjoying this deep dive into cutting-edge aerospace technology, don't forget to hit that like button and subscribe to the channel so you never miss our latest videos on the most advanced military hardware and the future of combat aviation. As established, traditional stealth coatings are ill-suited for the thermal environment of 4 times the speed of sound flight, and the aerodynamic shapes required for hypersonic efficiency, sharp, knife-edge wings and inlets are generally detrimental to radar cross-section reduction, which favors smooth, blended curves. This contradiction has led to persistent speculation that the MiG-41 will employ plasma stealth technology. The concept of plasma stealth relies on generating a cloud of ionized gas around the aircraft, specifically the nose and leading edges. Plasma is electrically conductive. When electromagnetic waves from radar encounter the plasma cloud, they interact with the free electrons, and depending on the plasma density and frequency, the radar energy can be absorbed and converted to heat or refracted and bent around the object rather than reflected back to the source. Russian research institutes have investigated this technology for decades. The primary advantage is that it allows the aircraft to be aerodynamically optimized for speed with sharp edges while still maintaining low observability when the system is active, meaning it can be turned on for combat and turned off for cruising or friendly communication. However, plasma stealth comes with severe penalties that make its operational viability questionable. First, generating a stable plasma cloud requires immense electrical power, further taxing the engines and power systems. Second, a plasma cloud is effectively a radio blackout shield. Just as spacecraft lose contact with ground control during re-entry due to the plasma sheath, a MiG-41 with active plasma stealth would be blind to its own radar and unable to communicate with friendly forces. Third, while plasma might absorb radar waves, it glows brightly in the visible and infrared spectrums, making the aircraft a shining beacon to optical and infrared search and track systems. It is a trade-off, invisible to radar but highly visible to thermal sensors, a dangerous gamble in an era of advanced multispectral targeting. The MiG-41 is unlikely to operate as a lone wolf. Following the doctrine established by the MiG-31, the PAK DP will serve as a data truck or a quarterback for a networked air defense force. Equipped with a next-generation active electronically scanned array radar and high-speed data links, it will patrol the upper atmosphere, utilizing its altitude to extend the radar horizon to 400 to 500 kilometers. Once a target is detected, the MiG-41 can distribute targeting data to other assets, cueing ground-based air defense batteries, guiding missiles launched by stealthy Su-57 fighters operating silently at lower altitudes, or directing combat drones to perform the intercept. This network-centric approach allows the MiG-41 to stay back from the fiercest fighting, using its speed and altitude to survive while orchestrating the battle space. Operating at altitudes between 40,000 and 50,000 meters, the MiG-41 sits in the near-space domain, bridging the gap between air and orbit, a unique vantage point that makes it an ideal platform for direct ascent anti-satellite missions. Launching an anti-satellite missile from 45 kilometers altitude bypasses the densest part of the atmosphere, reducing drag and allowing for smaller, cheaper missiles to reach low Earth orbit. This capability aligns with Russian military doctrine, which views space as a critical vulnerability of Western militaries, and the ability to degrade the enemy's GPS, communications, and reconnaissance satellite constellations at the onset of a conflict would act as a powerful force multiplier. The MiG-41, therefore, is not just an interceptor. It is an orbital denial asset, designed to blind the enemy before the first soldier crosses the border. While the technical specifications of the MiG-41 are formidable, The industrial reality of the Russian Federation casts a long shadow over the project, for the development of a sixth-generation fighter requires access to the highest tier of global technology. Advanced microelectronics for radar and avionics, high-grade composite materials for the airframe, and precision manufacturing machines for engine production. Since the invasion of Ukraine in 2022, Western sanctions have severed Russia's access to many of these critical supply chains. The Russian aerospace sector has been forced to cannibalize commercial airliners for chips and spare parts, and developing the proprietary domestic capacity to manufacture the radiation-hardened, high-temperature electronics required for the MiG-41 is a generational challenge. The Su-57 serves as a cautionary tale. Despite flying in 2010, it has struggled to reach mass production, with only a few dozen operational airframes delivered by late 2023, largely due to supply chain and manufacturing bottlenecks. If the Russian industrial base struggles to produce a twice the speed of sound stealth fighter in quantity, the leap to a 4 times the speed of sound hypersonic interceptor seems industrially improbable. This disparity between claims and capacity has led many Western analysts to label the MiG-41 as vaporware, a project that exists primarily to secure government funding for the Mikoyan Design Bureau and to maintain the domestic illusion of technological parity with the United States. The timeline provided by officials of first flight in 2025 and service entry in 2028 is widely regarded as fantasy, as a standard fighter program takes 15 to 20 years from concept to full operational capability. Given that the MiG-41 is reportedly attempting to break multiple physical barriers simultaneously in propulsion, materials, and weaponry, a more realistic timeline would place a first flight in the mid to late 2030s, with service entry in the 2040s. Beyond materials, there is a crisis of human capital, as the generation of Soviet engineers who designed the MiG-31 and its engines has largely retired or passed away, and the post-Soviet era saw a massive brain drain of aerospace talent. Relearning the expertise of sustained flight over 3 times the speed of sound, a capability that was mastered in the 1960s but largely abandoned globally due to cost and complexity, requires a continuity of institutional knowledge that Mikoyan may no longer possess in full force. The Mikoyan MiG-41 PAK DP stands as a testament to Russian strategic ambition, a machine designed to push the envelope of what is atmospherically possible. In its conceptual form, it is a terrifying adversary, a ghost that flies at the edge of space, too fast to catch, immune to conventional missiles, capable of blinding satellites and swatting hypersonic gliders with a shotgun of interceptors, effectively acting as the ultimate guardian for the motherland's frozen north and a technological embodiment of the Fortress Russia mentality. However, looking beneath the cowling reveals a project fighting a war on 2 fronts, one against the laws of physics and another against the laws of economics. The thermal challenges of 4 times the speed of sound flight require materials that are incredibly expensive and difficult to manufacture. The propulsion technology required to bridge the gap between turbofan and ramjet is notoriously temperamental, and the industrial base required to build such a machine is currently sanctioned, resource-starved, and fully committed to a grinding war of attrition in Ukraine. It is highly probable that the MiG-41 that eventually emerges, if it does at all, will be a compromise looking like the renderings but performing more like a Super MiG-31, utilizing a modernized airframe, advanced engines from the Su-57, and advanced missiles, but capping out at 3 times the speed of sound rather than 4.3 times the speed of sound due to thermal and propulsion limits, perhaps relying on long-range missiles rather than near spaceflight to achieve its kills. But even as a paper plane, the MiG-41 serves a strategic purpose, forcing Western planners to ask what if, and driving investment in counter-hypersonics and next-generation interceptors. In that sense, the MiG-41 has already achieved its first victory. forcing the adversary to spend billions to counter a threat that may never actually leave the runway. Whether it ever screams across the Arctic sky, trailing plasma and defiance, remains a question for the historians of the future. But for now, the MiG-41 remains the ghost of the stratosphere, the fastest aircraft that never flew, haunting the dreams of defense planners and aviation enthusiasts alike.